Hello, everyone. Thank you for coming to this Cronos information session. And I invited three distinguished researchers, Professor Serge Fdida and Professor Jim Kurose and Director Abhimanyu Gosain. So these three researchers are experts in defining cutting-edge research, and we are calling them now grand challenges in Cronos. And I'd like them all to share their experiences and what are happening in their regions. And so then you can consider defining your own grand challenges by listening to these experts' opinions about their research efforts. Okay, so after listening to all these speakers' talks, so then we can discuss, maybe you can do a Q&A with these speakers, or maybe I can interact with them like a panel discussion, and I would like to extract some more information, useful information from them. Okay, please welcome the first speaker, Professor Serge Fdida from Sorbonne University, Paris, France. Serge, if you are ready, you can, the floor is yours.
Okay, I think it's fine now, and good evening to everyone. It gives me really great pleasure to participate to this event, and most importantly, I'm very happy that I am associated to the Cronos project. I think it's a very ambitious project dealing with research, innovation, and service to society. So Professor Nakao asked me to address grand challenges in Europe. And actually, this is defined in Europe within some programs that are addressing so-called mission-oriented research and innovation. So the idea of this project is really to address important societal challenges, but also to deliver to society. And the best example would be, can we have a man on the moon? But again, you can see those programs as addressing topics such as the one you see on the right-hand side, halving the human burden of dementia by 2030. There is no such grand challenge in Europe dealing with digital sciences, but nevertheless, there are a lot of documents and groups that are dealing with how you can master Europe's digital infrastructure needs. Because obviously, this is instrumental in order to support future competitiveness of Europe in all sectors. And there are several instruments that have been developed by the European Commission in order to address those topics. And the maybe most important one is called the Smart Networks and Services Joint Undertaking, SNSGU, that I will mention a bit later. And if you look at those documents, of course, you will see a lot of typical challenges and issues, but I would like maybe to shed light on two of them. One is about the new articulation between telco and hyperscalers. And the other one is about the trend that the internet is becoming privatized. And it raised a lot of issues regarding sovereignty, for instance, with respect to submarine cables and data centers. So now, if we dig a little bit into SIG-G, so this instrument, SNSGU, Joint Undertaking, is organized under the umbrella of the SIG-G Industrial Association, SIG-GIA. And SIG-GIA is basically the voice, the European voice of industry and academia regarding the future development of the infrastructure, and in particular SIG-G. So you will see basically different activities dealing with 5G, this is stream A, SIG-G, this is stream B, so more, let's say, advanced research programs. Stream C are related to activities targeting experimental infrastructures. and Stream D are related to the vertical, so large-scale pilots addressing industry, for instance, addressing energy, agriculture, and so on and so forth. So if you look at the topics addressed, of course, you will see many, nothing very original in the sense that you will see similar topics addressed worldwide, such as time-sensitive networking, intelligent sensing and communication, AI/ML, of course, millimeter wave communication, virtualization of the infrastructure, and so on and so forth. And in Europe, the Commission likes, let's say, flagship project, and the so-called EXA-X project is the European 6G flagship project. It's a big project where you will find more than 40 partners, mostly driven by industry, but where you will see also academic. So this is basically the way Europe is paving the way towards 6G. And if I look now at what I believe are the most transformative principles that we have observed over certainly the last 20 years, they are related to the softwareization of the infrastructure. And because of this trend, it means that networks are cloud native, that we have to use a completely different set of tools in order to develop and deploy the infrastructure. And of course, in order to control the infrastructure. And because of the value of data, we expect that eventually we can also throw AI and machine learning at the problem. So basically, you will be able to address different types of topics. Of course, managing the complexity of the underlying infrastructure, be it related to spectrum, energy, and all other kind of resources. And because now we have this network operating system that is providing the gateway between the physical infrastructure and the services, we expect that we can develop the so-called apps that provide an agile solution to basically develop new services. But this also triggers a lot of issues that are related to software engineering, and basically how you can control who is going to integrate those solutions in order, on the one hand, to be able to manage it, and eventually to enforce self-management of the infrastructure, and on the other hand, regarding the control of the infrastructure. And this is also where you see some AI/ML solutions eventually being developed. So a lot of room for interesting research and application here. Now, Professor Nakao asked me to consider grand challenges that could be a framework for cooperation. And I will basically mention three, where I believe that there is a good balance between, let's say, advanced research efficiency and social value. So the first one is connecting the billions. I think this is still a problem to address, where we need not only to develop very advanced technologies, but also technologies that fit the needs of those unconnected in very difficult environments. Second one is about energy consumption. And likewise, in the past, we have been used to develop advanced solutions, very efficient solutions, without really considering the carbon footprint. And now, certainly, we need to see how carbon footprint should be considered in order to balance the architecture that we have in mind. And last, internet resilience. For me, this is becoming a huge problem because as for other assets, for instance, energy, they have been optimized with respect to cost. And we have seen what are the consequences. So I believe that we have to revise the organization of the infrastructure in order to include resilience as a key parameter. So as a conclusion, I would like to engage the participants and those who are going to be involved in CRONOS in international cooperation. This is really the way they can mature. This is the way they can understand diversity. This is the way they can also be associated to different practices of research, education, and innovation. I'm coordinating this European large-scale scientific instrument, SLICES-LI, and I believe that this is an appropriate platform and a catalyst for cooperation because it is completely open, it is inclusive, and I believe that this could provide some interesting opportunities for joint activities. So this being said, I will stop here, and of course, I'm looking forward for a discussion in the panel. Thanks a lot again for the very kind invitation.
Okay, so as Aki mentioned, I'm a professor at the University of Massachusetts at Amherst in computer science, and I'm actually in Paris right now visiting with Serge at the Sorbonne University. These are the kinds of panels that I love to participate in because it's a great opportunity. It's always really good to sort of step back and look at the big picture. And so I want to, we were asked to talk about some national initiatives, what we're doing ourselves, and what the future might look like. So I thought I'd start off. I no longer work at the National Science Foundation, but I spent 5 years there leading the computer science directorate there and spent a lot of time, since networking is my research area, a lot of time paying particular attention to that area, as well as, well, many other areas also. So I want to just put one slide up here about some NSF programmatics. I think Manu will talk about a bit of this in a little bit. But the first thing I wanted to say is that, a lot of times we focus on new things, what's the new shiny thing and the new great thing that we're doing. One of the hallmarks of NSF research is that we've always had what we call core programs. And that is, you have any idea in any field or any idea in networking that might be, say, not related to wireless, not related to AI, not related to things having special initiatives. There is always the networking, what's called the NETS core program. So networking, technology, and systems. So this program has been around literally for decades. It's the largest part of the NSF networking portfolio. And as you can see here, this is a catch-all for everything: novel frameworks, architectures, protocols, methodologies, experimentation, experimental approaches. The computer and network systems, which has two major programs, the NETS program and computer science computing systems research, their budget is about $240 plus $1 million a year. So that's just sort of the level of investment. Now, I'm going to leave this to Manu mostly to talk about, but since there's a lot of interest here in wireless, obviously I wanted to bring up the platforms for advanced wireless research, the PAWR test beds. There are 4. When I was at the NSF, the initial 2, PAWR and Cosmos, were underway. And then since then, in PAWR and Cosmos, 5G, RAN, orchestration, low latency, sort of really meat and potatoes, as we say in English, meaning sort of core, central, broad areas that are covered in those 2 test beds. And since then, an aerial wireless test bed and a test bed for smart and connected rural communities there. And one thing that I'll point out is, I've seen this in Japan, I see this in France, I see this in the United States, this notion of public-private partnerships. So there are a number of companies. Matter of fact, when we put PAWR together, NSF and the private companies were 50-50 sharing equally in PAWR. And then finally, there's a RINGS initiative that some of you may have heard of. Again, this is an academic industry consortium that goes sort of up the stack. And I think the hallmark of that is the collaboration between industry and academia. Okay. I'm a participant in one of the co-PIs on an AI institute that's funded by the National Science Foundation called AI Edge. In 2019, the National Science Foundation started funding AI institutes, which are generally a consortium of universities with industry partners that focus on both foundational AI as well as AI in particular, applied AI in particular application domains. And there's actually 2 of the 25 institutes, AI institutes are in networking, and both of them are actually focusing on the wireless edge. And the one that I'm involved in is called AI Edge. It's led by Ohio State University Neshroff. And our mission here, I mean, this is a broad one, right? But it's not just research. So research is really our bread and butter, but also education, knowledge transfer, workforce development. Here's a picture of the way we sort of structure ourselves within the AI Edge Institute. I should also say that these last for 5 years. At the foundation, there's the foundational theory for AI and machine learning in particular, really, but also LLMs, and their application in the area of wireless networks. So we talk about AI for networks, and think of that as control and management. So the domain is networking. We're using AI techniques to do resource allocation, for example, or monitoring and management. The other part we call AI on networks, and that is federated learning, the distributed computation that goes on within AI systems when you're integrating devices over a wireless edge back to a core. So we've got, I should say, 8 projects going on in those areas you see here. Not time to go through those. Something I want to point out, some of you who I've worked with in the past know that I've been also involved in an NSF Engineering Research Center. And the idea there is at a high level, you want to take the research you're doing and you want to instantiate it in test beds and touch real applications. And we're doing that also in the context of AI Edge, thinking about ubiquitous sensing and networking in a number of different domains. And so we're working with partners there as well. Okay, I think I'll skip this. I want to close. I want to take a really big picture view of things, and maybe we can talk about this later. But as I look back on computing and networking and telecommunications as part of that, I identify sort of 3 phases of where we've been and where we are now. And the first phase is what I want to call the artifact phase, and I think that lasted, up until the late 1990s. I mean, it still goes on. But for the first 30, 40 years of computer science, there was a lot of emphasis on building the operating systems, the networks, the databases, and some of the theoretical foundations there. I would say that, honestly, because of networking and the emergence of planetary scale systems connected by networks, that the middle age, if you were, the second phase was this notion of building systems and applications at scale. So the internet, searching on the internet, the web came into being, social media, data center applications. And that, that really hit the ground running, say, 2007 timeframe. I will say, and, I heard Serge use the phrase mission-oriented, that I think the phase that we're in now, and this is broadly across computer science, but I think it's in networking too, is an emphasis on people. So information, human augmentation, a lot of the AI and the LLM things that we're seeing now, privacy, computing for the common good. And I think that's where we are now. Now, I want to tie this big picture from artifacts to systems to people to our area, which is networking, right? And so everybody knows, pre-2000, we had the protocol stack, these colors here on the left-hand side, sort of show how much emphasis there was there in a particular layer. We were focused on the network. 2000 to 2010, distributed applications, mobility starts coming to the fore, security starts coming to the fore, application level infrastructure, clouds, content distribution networks, things like that, really up at the application layer are really hot topics. And then I'd say from 2010 to now, software-defined networking, mobility, again, security, and privacy. And what I see there is that also an increased emphasis on management, configuration management, network management, and the experience of the users at the edge, QoE rather than QoS, for example. And so I think what we're seeing is probably not many of you are old enough to remember when the internet was, or networking was first getting started, and we were layering on top of the phone network. And now we're layering on top of the internet, and the problems are going up the stack. And so when I think about long-term, where are the challenges, I see these challenges moving up the stack. So moving away from a technology push, I mean, especially in wireless, we still have some technology push, but really moving more towards application pull. Serge mentioned mission-oriented. And here's a quote I wanted to share with everybody. Many of you know or know who Larry Peterson is. He writes some wonder. He and Bruce Davey write this blog that I really, really love a lot. And he wrote a piece in September called What I Did Over My Summer Break. And one of the things he did over his summer break is he went to a couple of workshops. And he had this perspective in there. The key to doing impactful research in mobile networking is to have a compelling application domain. And that, to me, really resonates with this notion of application pull, that the research problems that we're seeing at the edge and in the core and networking are more and more being driven by the needs of the application. So to summarize, and maybe we'll get a chance to talk about this more, obviously many research opportunities in current and next-G wireless systems. When I look across, let's say, multiple administrations in the United States, I still see continued broad interest in the funding agencies. I see that internationally. Clearly, AI and ML in next-G systems. This notion of collaboration between government, academia, and industry, and quite honestly, what government and academia think about, government and industry think about is much more this pull than the push, I think. There is, for us as researchers, the curiosity-driven research. Those are like the core NSF programs, as well as this use-inspired research. So, a couple questions that I've been thinking about a lot recently. We hear a lot about next-G or 6G or 7G and beyond. I think if you think about application-driven and use-inspired or mission-oriented research, there are still a lot of challenges with what I might call current G. And I think that has to do a lot about getting out there in the field and working with real applications. The question, of course, is how do you then work with real applications? So we've got these wonderful PAWR test beds, but my great hope is that private 5G, mobile networking, and sort of the kinds of coverage and technologies that you have in enterprise cellular networks can now be enabled in the context of private 5G. We'll see that being implemented in our universities and institutions at the edge, and that will give us additional access to wireless infrastructure for research. Okay, so with that, again, thank you. I'm really looking forward a lot to the conversation that we have again, and thank you, Aki and others, for the opportunity to speak here.
Yep. Am I coming through now?
Yep.
Okay, perfect. Thank you so much. So yeah, good morning, good evening, folks. Thank you for having me again. Just wanted to echo my thanks as well to Professor Nakao and the rest of the team. So I'll build off of what we've heard so far from Professor Fdida and Professor Kurose, and I think that's a nice framework for me to give you an update on where some of the work and some of the perspectives that I bring, wearing a few different hats that I have. And I'll broaden the aperture, at least from the US side, beyond the National Science Foundation, to incorporate some of the perspectives from multiple other US agencies that are in the field of networking and communications, and some of the programs that have been brought to bear looking ahead over the next 5 to 10 years. But let's sort of just take a step back. Just wanted to sort of add my commentary to this whole 5G, 6G story and play. And I think I completely concur with the focus on the current G, because the reality today is the networks that we are all using are about 24 months behind what standards, and that's in air quotes, 3GPP or other agencies are defining and developing. So things that exist in the literature are not what is available in reality, and there is a reason for it, especially in the 5G domain, which is we still don't have a killer app. And that's where majority of the focus is in terms of trying to set up what kind of application domains 5G is going to enter. So whether it be the private network, whether it be different industry verticals, whether it be the consumer enterprise side, still remains to be seen. But the juggernaut that is 3GPP and standardization has to continue to move forward. And we are now, completing release 18 and 19 study items, which is really good. But really, the notion is that we still have to kind of focus on bringing the perspective of what we've achieved in the networks of today, and how do we sort of monetize them to meet the needs, both from a societal perspective, a technology KPI perspective, or a technology value perspective. So you've heard a little bit about PAWR. Again, I won't go into detail of each platform, but I think the main takeaway, or the main addition I want to add to what Jim had said earlier, is this notion of application domains. So there are technology domains that each of the test platforms, and again, this is a public-private partnership program set up between the Science Foundation and 30 industry partners. We're coming up on 8 years of building these test platforms at scale. But the application domains here primarily are on the PAWR side, mostly around coverage. So that's sort of the macro area that I would say from an application pull perspective. How do we increase coverage? How do we use massive MIMO systems, software-defined networks to increase coverage? Cosmos, more about capacity increase. So we're looking at millimeter wave. We're looking at optical backhaul. And how do we sort of get data in a dense urban environment? And what are sort of the technologies that build? AirPower is more about mobility, and that's more about unmanned aerial systems, but also unmanned ground vehicles. So how do you solve challenges of high-speed mobility in the domain of drones and UAS and counter-UAS? And then on the rural side, we're looking again at application domains primarily on the ag tech side. This also has some resonance with coverage, obviously being large swaths of rural areas. So they're looking at things like free space optical communication. And this is the physical infrastructure. We also have a digital twin infrastructure called Colosseum, which is the largest RF emulation and network emulator that's available at scale. And that complements this physical infrastructure by allowing our research community to actually emulate things at scale. And that's housed here at Northeastern University in Boston, Massachusetts. Okay, so what powers, unintended, the end-to-end programmable infrastructure, and what's the architecture that we, the research community and industry, are coalescing towards? And for us, open source, and that's just, we use the word open, but I'll go deeper and call it open source, has become very important. And as you look at a mobile telecommunication system, all different elements over the past 5-7 years, again, due to what Serge talked about, softwareization, virtualization, programmability, controllability. We now have a best of breed across each different element. And what we've been able to do with PAWR is we've been able to build this into an end-to-end system that's available for you, any researcher out in the global community, to instantiate with a click of a button. And that's very powerful. And that now takes away the burden or helps you build an on-ramp from a workforce development perspective, which I'll get into as well, which allows you to really start to educate. So gives the power back to the educators, because now this complicated infrastructure and system is available to them to use as a teaching instrument. It's available to researchers. And from our perspective, we're able to support multiple open source community ecosystems that are contributing to these different elements. So I'll switch over now, go a little bit deeper, maybe using Jim's framework of application pull versus technology push. So now I'll switch over to the technology push side. The key piece that is a U.S. government named priority, both from the White House and the Office of Science, Technology, and Policy, is around Open RAN, or Open Radio Access Network Systems. So this is kind of a pictorial representation of how the Coliseum infrastructure, and extrapolate this into how our power platforms also accommodate a Open Radio Access Network architecture. So this is a disaggregated radio access network with multiple different elements, the control unit, distributed unit, radio unit. And I think the power of the radio intelligent controller that sits at the application layer or at the service management and orchestration layer allows you the power of controlling the underlying infrastructure while being abstracted away from the complexities of the underlying infrastructure through the use of APIs and open interfaces. So Open RAN also enables this new domain, and we heard about the AI Edge Institutes, which Northeastern University is also part of the AI Edge platform. But we're also very proud to be part of the AI RAN Alliance that was recently formed as one of our founding members alongside University of Tokyo. So some of the founding members are listed on this slide, but what we are actually focusing on is how do you bring the paradigm of AI, ML, LLMs, data models, and how do you sort of insert that into the radio access network? So how do we sort of leverage the power of the infrastructure? How do we build optimization? How do we build AI applications that are embedded into the RAN system? And how do they enable a radio access network of the future? And this is sort of broken down into three basic elements: AI and RAN, AI on RAN, and AI for RAN. And that's something that is really, really key. And I think it brings two really disparate communities, the AI community that I will lump together in more of a compute paradigm, and then the radio access network that's more on the digital signal processing as well as on the networking side. And we're kind of working quite closely. Little bit of our connective tissue with the AI RAN Alliance. We're focused on AI-driven spectrum sharing, which is going to become very important for 6G because globally, I think there is consensus that there is no clean spectrum that's going to be available for 6G. So spectrum sharing is going to be a native paradigm. And we are synced up also with the O-RAN Alliance, which is sort of the de facto place for where the Open RAN specs are developed. Just to be clear, AI RAN Alliance, is not going to become a standards development organization, but it's going to inform what community organizations like O-RAN Alliance and the 3GPP domain are going to do. So this is more of a technology enabler, and we are bringing to bear some of our AI-ready lab and testing capabilities, as well as the orchestration of AI/ML on RAN workloads. And this will culminate with the demonstration we're preparing for Mobile World Congress in 2025. So this is sort of what you're seeing on your screen, sort of flashing a spectrogram of what we're able to capture out in the wild, and then how do we sort of predict or do an inference on a spectrogram out in one of our power test sites. Again, I won't, in the interest of time, just leave this here. You'll have the slides, but the key piece here is the ability to build a CI/CD CT tested environment for enabling AI elements in different parts of the network. So whether it be the radio or the edge or the core, or all the way up at the service management and orchestration layer. Okay, so let me quickly switch topics to what else are the US government priorities. This is a program that I support coming out of the NTIA, or the Department of Commerce in the US, called the Public Wireless Supply Chain Innovation Fund. It's about a $1.5 billion grant program, and that's important to understand. It's about grants, which is to stimulate research in a much more free, open fashion from this agency. And the idea here is to promote open radio access networks and deploy and commercialize this technology. And this was all funded by the CHIPS and Science Act of 2022 that was funded by the US Congress and the US government. So what have we done so far with this? We've released multiple funding opportunities, primarily focused initially on accelerating testing, conformance, and performance. And we put about $140 million in grant awards for that. And the second one is about developing open radio access, open radio units. And this is about encouraging hardware innovation. So this is about building efficient power amplifiers. This is about building the best generation, next generation software-defined radios. And here we're going to spend about $420 million, and you'll hear some of these award announcements come out in the next week. Coming soon, we are focusing now on the application side. So we're going to be looking higher level on how do we stimulate the Open RAN ecosystem and how do we impact different verticals and different application domains, leveraging the testing and the innovation we have already supported in the radio as well as in the testing side. Last but not the least, I wanted to talk about another sponsor and program I support, which is out of the US Department of Defense, which is working on building, and let's go back all the way to the technology push, a completely open source, Open RAN enabled ecosystem called Okudu. So this is about building a best of breed open source softwareized implementation that will work with a underlying open hardware system. So think about the different forms of compute that today you can use to instantiate a mobile communication network, whether it be a CPU, a GPU, or an FPGA. And what this program is going to do is it's going to build an abstraction layer as well as the software implementations of a CU, a hardware accelerated distributed unit, and connect that to the underlying infrastructure or the hardware through the various advances we are seeing in component technology and silicon on chip, or materials like gallium nitride, silicon carbide, and how do we sort of build that entire stack, again, building off of what Jim had talked about, all the way from the underlying hardware, the abstraction layer, and the software. And this is going to have a strong impact on the global community because this is going to be open source, available to all our partners, including those who are here on this call. So this program is scheduled to kick off in December this year, and then we have about a 24-month cycle before we start releasing stuff out to the community. Okay, last but not the least, global areas of cooperation we can talk more about in the panel. The thing that I want to really focus here on is on resilience, and that's, to me, an application domain. So resilience is going to become very important because everything we've talked about so far, and given where the global community is being, whether it is about connecting the unconnected, whether it is about public safety, whether it's about resilience or reliability when you have natural disasters, which both of our countries, the US and the Japan, have unfortunately have to encounter this year. So we want to talk about resilience, clearly. And then one component technology that I'm very interested to explore would be the sub-terahertz domain. So this is about how do we build increased capacity, and this is more of the forward-looking 5-year, 10-year horizon, and how do we sort of make large frequency access available, and how do we build technologies at a feasible, cost-effective scale. So I will stop there. Again, appreciate your time, and then look forward to the panel discussion.